This crankshaft has balance weights on it, which is different to the 350 Sunbeam. The 350 Sunbeam isn't balanced at all, but they'd learnt a bit by this time. So I'm just about to fit the last of the balance weights to the crankshaft, and this is the balance weight here. Like everything on this, it's beautifully machined, so everything just slides together. Here's the tab washers, so we've got to fit one of those to the bolt. That then can go through the crankshaft. It's a nice tight fit again, so I'll just tap it with a soft hammer. And then I can put the nut on from that side. No, before I do that, I better put the other tab washer on, hadn't I? That's got it. It's got it started there. And then the bottom side of tab washer, there's another bolt which I've just got to line up. In fact, it looks like it's gone straight in. Sunbeam did have a habit of using a fine metric thread as well. Whitworth and some of the other pieces, but mainly BSF. But we're always getting caught out with the finer threads, you know, so we have to check it. I mean, it's not quite BSF, it's not quite metric conventional, so it's a metric fine. If it's not that, it's something that Sunbeam have used themselves. They've produced their own threads at some point, I think. I don't know why, but Louis Coastland was French, so he has, you know, affinity to metric threads. I mean, he worked for Peugeot before Sunbeam, and you know, a lot of the technology came from that side of the channel, basically. The twin cam arrangements and things. Peugeot twin cams were very good engines. And he's brought all that knowledge with him. So, there we are. That's basically the weight on. I will go round properly and check them before I fold any of the tab washers over. But that's that done. So the next bit I want to do is the last of the sludge traps. So there's the caps for it. It's very similar to a lot of crankshafts of the period. Rolls-Royce used it all the time with these tapered caps. So all we need to do is pop that through there, put the cap on the other side, pop that in there, put the nut on, make sure it's all nicely centralised, otherwise it won't seal. It's got to seal on these taper washers because there's quite a lot of oil running through the crankshaft. There's a lot of space, so there's a lot of oil all being pumped around. You've got 40 to 50 psi of oil all through the crankshaft, so that's a huge volume of oil. So the pumps do a lot of work, and if you've got a leak, the oil will be coming out of everywhere. So and if the oil pressure disappears, that's bad news, you know. So we don't want that to happen. So that's the last of those. All the balance weights are on. The next thing I'll want to do is check all the com rods on all the big end journals, make sure they're all free and fitting, clean, before I put the crank into the crankcase. So that'll be the next job I want to do, is fit that number 1 bearing on here. It's difficult to see, but on the inside the piston, there's actually when they made the pistons, there's a lump right in the middle of the crown, which is a pad that actually sits against the gudgeon pin, which is this pin here. When that comes out, put the gudgeon pin in, and that pad goes through the end of the con rod. So some of the combustion forces that are going through the crown of the piston go straight through there onto the gudgeon pin. So it helps save any problems with the crown of the piston. So it's not going to deform so readily under the explosive forces of combustion. So I've not seen it on any other engine, but it's sort of, I don't know if it's unique to Sunbeam, but it's certainly very rare. Okay. But the oil drillings are all through here as well, so all the oil that gets up onto that little end and onto the gudgeon pin is it's all coming from the crankcase. It's all that's been splashed around inside the crankcase and up the rods. There's no pressure feed as such up the rod through the rod up into the little end, so it relies on oil being splashed around within the engine to lubricate that. On a Silver Ghost, for instance, it's got a pipe that runs along the inside of the con rod there, and that is pressure fed up to the little end bearing. But these, they didn't have that, so it's splash fed. That's all it is, and that's why a lot of these drillings are all for, to get oil up in there. On the 350, we had to remanufacture pistons. In fact, we got them from America in the end. We sent a pattern over, and I requested that they were flat top pistons, just like this one, because Campbell had new pistons made for the 350, and he put a raised crown on them to get more compression, get more power. We didn't want that, so I asked the Americans to make flat top pistons. When they came back, they had a nice dome piston, so it's too late by then. We had to live with those. So, but these are the original ones out of this engine. The only thing that isn't original is the piston rings, because when we took the rings out of these grooves, none of them would come out intact. They were all glued in there so tight, with the old Castellar had turned to a Loctite type material, and we just couldn't get them out. We tried heating them, flexing them, trying to flush the oil out of it, and it just would not work. In the end, every one of them broke. So we're very lucky in this country. There are still a few people about that can make decent things. I mean, so there's a chap called Clupit Ring Company up in Barrow-in-Furness. He made the rings for us. Sent him a pattern again, measured it all up, and we've got a complete set of rings for both engines. They are exactly the same as they were when they were fitted in the factory. And as we've said before, these engines haven't done a lot of work. They never flew, well, not this one anyway. It did go swimming in Detroit, but other than that, it's done no work at all, apart from when it went up and down Daytona Beach. So they're almost brand new. How do you get two con rods working off a single journal? Well, your options are either you have a master and slave configuration like this, so that when it's going round the crankshaft, the con rods are going up and down the bores. Your other option is what Merlin or Rolls-Royce have used, is to have two skinnier rods that run alongside each other on the same journal. Whether Louis Coatland considered that or not, I don't know. I would think that the thinking was that they've got a nice broad bearing surface on the bottom of the con rod, gives you a stronger rod assembly. And Napier did a similar thing. They did a broad arrow engine, the Napier line engine, where they had a master rod, and they had two slave rods running off the same journal. So space saving again over the length of the engine, especially for aircraft engines. You don't want a huge engine out the front, so they were trying to make it as compact as possible. So you had 3 rods on that particular engine running off the same journal. But Sunbeam decided to keep it with 2, which is fine by me. It makes it easier. You'd think that one stroke would be different to the other because it's running off centre of the journal. But the way it's calculated, in fact, it is the same. The strokes on both cylinders are the same. I wasn't convinced originally, but a very clever man by the name of Alistair Lyle, who worked for Cosworth, drew it out for me and explained to me exactly how it works. Because you're thinking it's running, you're thinking of the centre of the journal as being your pivot point, but actually it isn't. It's sort of that position there on the rod is when it's going up and down the bores. You know, it's it takes a bit getting round, getting it in your head. So, but that's the way it works. And Alistair, you know, very clever man. So I trust him implicitly over that. So, and he's shown it to me when he drew it out. So it's very, very good. It was all done on a drawing board, but clever people back in 1918. You know, you look at the materials they used. The machining was phenomenal, and the design was incredible. You know, they were able to come up with some very good ideas. So clever people back then. This is the front of the engine, depending on which way it is in the car or an aeroplane. This would be the front of an aeroplane. So on the end of here, you'll see this flange here and this bearing here. This is non-standard to the aircraft. This has been adapted for the car. So this whole lump on the end of the crankshaft is specifically to mount the flywheel on. And then that then goes on to the drive shaft, which then goes on to the gearbox, onto the spur gear, etc. So this is non-aircraft related. So that's been machined, fitted, put onto the end of the crankshaft, then the flywheel. And this flywheel doesn't look very big, but this, you'd think it's just a lump of steel, but I don't know what it is, but it's incredibly heavy for the size. Again, we've got no information of what it is, but you know, you can just about pick it up. It's very, very heavy. So that would be different to the aeroplane. So normally on the end of the aeroplane, you have this coming out here, and you'd have a gear on the end of it, which then drives another gear, a reduction gear it's called, which then comes out, and then the propeller goes on the end of there. So it just reduces the speed of the propeller, because if you have it going too fast, then the tips of the propellers are going far too fast and you can damage the propeller. A classic aeroplane, the Harvard at the moment, you can hear there's a very distinctive noise from the propeller, and that's because the tips of the propeller is supersonic, where it's spinning around so fast on that diameter. So to reduce that, they have a reduction gear, comes out the front of the engine, and we've still got all that on the crankcase. The gears aren't there, but all the housing and the original bearing is all in there still. So, but it's just blanked off, and out the bottom of the engine comes this bit, which then goes onto the flywheel, then onto the gearbox. This is the crankcase to the Beaulieu engine. Upside down at the moment, obviously, because we're working on the crankshaft area, and these are the main bearings. The crankcase has been machined. Then we have a bearing cap that has white metal on it, and then machined. Well, the whole engine is line bored once they're all in. So you fit the bearing cap into the casing, and then you've got the top cap, which has also got a bearing shell in it as well, which then sits down and then that traps the main bearing journal of the crankshaft. There's a cap that goes on the top, a little spacer, and then that's a nut and a lock nut and a split pin. So, you know, they don't want it coming out or vibrating off or anything. So again, the torque wrench settings for this aren't particularly high, they're quite low, 40 odd pounds, foot-pounds again. So but it's quite a well constructed crankcase. It's a 9-bearing crank assembly, so, and that supports the weight of the crankshaft, stops any flex in it at all. This is what is the timing gear end of the engine. So once we've got the blocks on, then we can start fitting all the timing gears that go all the way up to the camshafts at the top of the engine. So all these little pivot points are for various gears that drive the ancillaries. So you've got the water pump drive, you've got all the oil pump drives on this end as well. The oil pumps sit out here. Scavenge pump sucks it out the sump and then returns it back to the main oil tank, and the pressure pump then feeds into the end of the crankshaft through the main oil gallery here, which is a drilling that goes right along the crankcase, right through one end to the other, and then that all goes through into the main bearings through there. There's an input pipe on this side of the engine, so it comes out of the pump into this input, that's then casting into that main gallery, and then it runs away all the way along that gallery. And there's an oil pressure relief valve there as well on this side of the engine. And then there's a taking off for the camshaft oil feeds, which is at a lower pressure than the main oil gallery. So the main engine runs at about 40 psi and the camshafts run at 15 psi, so you're not spraying gallons of oil into the top of the engine, so it chokes the engine. So same as the 350, exactly the same pump, same design, exactly the same. There's 2 temperature gauges, one for each engine, and there's a single rev counter. And you only need a single rev counter because when the engines are coupled together, they're both doing the same speed. So there was a rumour that Seagrave wanted more instruments added to the dashboard to say that, you know, made it more complicated, but that never happened. Basically, it's just a rumour, a myth. So the only other pressure gauge on the dashboard is the fuel pressure gauge, because it's a pressurised system for the fuel tank. You literally pump air into the fuel tank and that pushes the fuel into the carburetors. But that's only running at about 1.5–2 psi. There is a little compressor on the end of the rear engine that does that. Initially you do it by hand, same way as we do with the 350. There's a pump on the side of the car, you just pump that up. That feeds fuel into the carburetors. Once it's started, the pump on the engine maintains it. Nothing unusual, a lot of the cars were using it at the time. And that's regulated to 1–1.5 psi, just enough to get the fuel out and into the carburetors, because normally the fuel is lower than the carburetors. So that's all it did. But this has got a 28-gallon fuel tank, so that's one run. Fill it up, turn it round, come back again. So they only had the tank big enough to do one run, really. You don't want to carry any more fuel than you need to, same as F1 today, minimum amount of fuel. The first few miles is to get it up to the speed, through the measured mile, and then slow it down again. And that's why they went to Daytona rather than Pendine again, because there's not enough room at Pendine to get it up to the speed they required. So they needed a longer beach. Yeah. And after the beaches, they then went on to Bonneville and places like that. The front engine has a clutch, so that's how they managed to achieve that. Plus, it also helped for starting the front engine, because you disengage the front engine from the gearbox, from the transmission, fire up the rear engine on the air start mechanism, get that running nice and smoothly, engage the clutch on the front engine, that then starts the front engine, and that you've got the slip of the clutch to allow it to synchronize itself. So any differences between the engines is taken up by that clutch. You have to have them running pretty well the same. There's not a lot of adjustments on these engines, you know, the carburetor adjustments are minimal. Plenty for altitude, but you know, but nothing for slow running or mixture control. It's set basically. So long as the engines are set up the same, they should run at the same speed. You can do a lot of damage to a clutch in a short time, but that's perfect, absolutely perfect. Nothing wrong with it at all. So it's just a matter of cleaning it, putting it back together, which is what we've done. Now that we've got all the bearings in the crankcase, I'm happy the way they're sitting. So I'm going to take all the caps off again, take them out the way, then lower the crankshaft into the crankcase, put all the caps back on, tighten them to the designated torque wrench settings, and then check that the crankshaft is turning nice and freely, which I can't see there being a problem with. It's all been line bored when it was done, so that shouldn't be a problem at all. You may get a bit of deflection in the crankcase without the blocks being on there, because they all help hold it all together in one place, but I don't think there's going to be any problem there. Put all that in, spin it, make sure I'm happy with that, take the crank out again, fit all the rods to the crank, and then just drop it back in with various people holding rods down all the holes so that we can get it all in there. Clamp it all back up together again, and then we can turn it over and start building the top end of the engine, lowering the blocks onto it, then all the camshafts after that, all the timing gears, pumps and everything else. So this is the important part. Get that right, everything else will follow. And as we were saying about the crankshaft, which comes out at this level on the crankcase, and at the back end there was a spur gear originally for the aircraft side of things, which ran inside this area here, which then reduced the output of the engine for a propeller that came out the bottom end of the crankcase here. Well, I say the bottom, it would have been the top when it's up the other way round, and that reduces the speed of the propeller so it's not overspeeding. Imagine these wooden propellers whizzing round at thousands of revs, you know. It's amazing how well they survived, you know, because even the Spitfire had a wooden propeller originally. In fact, a lot of them still do. It was only later in the war that they started producing aluminium propellers.